we have looked at the circuit model and one of the applications, quantum teleportation. Now we are ready to look at many other quantum algorithms, but before that, I want to introduce the query model of quantum computing. You already have been introduced to this model in some sense. Remember, in the case of Deutsch's algorithm, we said that we have a function f which we thought of as a black box, and we wanted to minimize number of calls to this black box. This was one example of queries where every time we asked a question to f, this was counted as one query. Let me formalize it. The reason being, many of the known algorithms for quantum can be formulated in terms of query algorithms. It has been used many a times to describe the most famous algorithms of quantum computing, and it gives lower bound on time complexity. In many cases, that bound is pretty good, and that's why we are interested in finding the query complexity of functions. What do I mean by finding the query complexity of a function? This is what we want to describe. This is the target for this video. If you remember a classical computation or quantum computation, access to input is assumed to be free. We never say, oh, you are asking for input so many times, it will cost you a lot. But if you think about it, any algorithm which queries the input a lot of times has to be expensive. This gives rise to query complexity model, where we only charge for accessing the input. All other calculations are free. This might seem surprising to you, but the model has proved its effectiveness by experience. So trust me on this and look at the model. I will show you many results which are very non-trivial and very important results in quantum computing, which are obtained using query complexity. Hence, we should focus on this model carefully. Remember, we are only counting queries. No other calculation carries any weight or is expensive. What is queries? Number of times we ask certain index of input. Classically, if I want to compute a function like this, if I'm interested in computing this function, then my input is a string of length n. I can think of it as x1 to xn. My input was x, my target is to compute f of x. In that case, whenever I make an algorithm, the algorithm at certain point of time would say, give me x2, give me x10, then some calculation, give me x1, and so on. Any algorithm will look like this. And we are saying that we will only count the queries here. The number of times we have this give me xi kind of an instruction, that will be the cost of the algorithm. and our only task is to minimize the number of times we ask this. That is called the classical query complexity. We also call it deterministic tree complexity. If you are familiar with it, if you are not, it's not a cause of worry. This was classical query complexity. What about quantum? The model stays almost the same. We will have queries and then some unitaries. No cost for them. This will not concern the input. They will just be applying plus on input. We know some bits. We are doing addition, multiplication, factorization, whatever. That will be the unitaries. That will have no cost. Only cost will be of queries, which is finding the input. What kind of queries are allowed in quantum? And the answer is already been given to you in Deutsch's algorithm. Remember, the oracle had two inputs. Just with one input, the oracle does not remain unitary. In this case, the oracle for x is something where if you give an input bit b on which you want to, or sorry, if you give an index I and workspace register b, you want to figure out what is xi. Then actually the value is computed in the workspace. This oracle is also sometimes called O of x. The action of O of x on I comma b is I comma b plus xi. This is how I define a quantum oracle. Quantum query oracle. This is the oracle whose queries we want to minimize. Notice that if you read about classical quantum simulation of classical circuits, this is in that spirit where when we simulated x comma y actually went to y plus fx. This is in the same spirit as that. Now we are saying that we have an oracle OX which hides whatever you want to compute, whatever is the input, and that will be given in the second register. Again, this action is only on the classical basis. You can always extend it using linearity. If we want to find xi, we will give I comma 0 as input and we will obtain I comma xi as output. This is called the address. This is the bit which you want to query, and 0 is called the target. In other words, the answer gets XORed to the target. This is the action of the oracle. From the part where we talked about quantum simulation of classical circuits, you can convince yourself that this is a natural way to represent an oracle. Remember, our input was of size n. Most of the time, we will assume that n is equal to 2 to the k. This will imply that address is specified by k bits. In this case, this will be k qubits and this will be 1 qubit. My address register will have k qubits, my target register will have 1 qubit. A small note here, clearly any algorithm, if it is doing t queries, then it will take at least omega t time. because every query will require some amount of time, some constant amount of time. So a two query algorithm will take omega t times. That means query complexity gives a lower bound on time complexity. Though we have to be careful, since they are not equivalent, we will also remember that separations in query complexity model do not imply separations in time complexity. This is sometimes people ask that, oh, we showed that quantum is so much more powerful than classical. Why do you say that this is not true in the Turing machine model? This is the reason, because we have shown the difference in number of queries but not number of times. It tells you something about the time complexity, but they are not equivalent. So exponential separations in query model does not give you exponential separation in the standard model. Remembering these 2 points, let's talk about once more the oracles which are allowed. Remember, this was the action of the oracle. Many a times, this oracle is written slightly differently. You will notice that if this I give as state minus, then OX prime, I'm sorry, I should say OX of I minus is minus 1 to the xi I minus, and OX to the I plus is I plus. Using these, you can show that I can use Hadamard to convert OX to another oracle OX prime, where OX prime on input computes the answer in the face. Sometimes we will talk about the oracle which was given on the top. Remember its action, which computes xi as an XOR. This is first kind of oracle, but that is same or equivalent as the second oracle, and depending on our application, sometimes you will apply second oracle, sometimes you will apply first oracle. Actually, it turns out there is a third kind of oracle which is also equivalent, which does OXI is minus 1 to the XII. B is not needed, but now I will, instead of ranging from all the addresses, it will go from all the addresses plus 1. It will have one more state. You can think of, if the addresses are 1 to n, instead now my I will take value 0 to n, and then OX of 0 will be just 0. You can also show that this is similar oracle to OX and OX prime. All these three oracles are query oracles. We can assume we have, when we are solving query problems, we can assume that we have any of these. They are equivalent. You might have a question of how Deutsch's model was in, sorry, I should say Deutsch's algorithm was in query model. You can observe that they are the same things. If I write my input, remember I wanted to compute n to the 0, 1 my input was x1 to xn, I can view it as a truth table of a function g from 0, 1 to the k to 0, 1. Again, this will happen when n is equal to 2 to the power k. If I assume this, then I can say that at I correspond to some binary string b1 to bk, so xi is g of b1 to bk. This is what I mean by saying that input is written as a truth table of some function. Then instead of hiding ox, I can say that I am hiding g. And given I is equal to b1 to bk and some work register, I will obtain b plus xi, which is same as b plus g of b1 to bk, which is same as b of b plus g to I. These are various ways to understand the query model. I can view my input as a description of a function itself, and then I want to compute a property of the function. Or you can say, like we said in the start of this lecture, that I just want to compute a function from 0, 1, comma n to 0, comma 1. Now remembering this, in the next video, we will generalize Deutsch algorithm to Deutsch algorithm and show separation in the query.